chemistry. Heat energy can be transferred from hot to cold. Okay, so it does actually have a direction of travel. So when we look at heat energy, we always look at different concentrations of heat. So let's start the lesson today by examining how heat can travel. So heat is a form of energy that travels from hot to cold. We say that heat energy exists across a gradient. What that really means is heat energy doesn't require any additional energy for it to move from one place to the other. It just does it naturally. So if we look at examples of how heat travels, okay, let's start by drawing a fire. So let's say this is a campfire. We all know that campfire will give off heat into its surroundings. Now, no one's going to argue that fire is hot. And all this radiant energy, this heat energy, is leaking into its surrounding environment. Now, suppose there is a person sitting right here. I'm not a very good artist, but I try. So if this person is just sitting by the campfire here, and he's feeling really, really cold, sooner or later, all that heat energy that's coming from the fire will eventually go into this person as well. So what this person feels is warmth. But in order for this person to feel warm, he or she has to be cooler than the fire itself. So in a sense, this person is cold. So when you have less heat energy present in an object, okay, that object will naturally become warmer. And the reason for that is because of our heat gradient. As fire leaks out into the environment, okay, anything that's cooler than it will tend to absorb that fire, or that heat, sorry. So if it's absorbing heat, we have a name for that, okay? We call it endothermic. Okay, so if something is going through an endothermic reaction or an endothermic process, they're absorbing heat. But any substance that releases heat to the environment or to another object is going through a different process. So let's say that this campfire here is releasing heat. this is called exothermic. I usually think of exo as in exit, so you're leaving something. So you have exothermic reactions and endothermic reactions. And these kinds of reactions exist naturally based on a heat gradient. So let's take a look at these endothermic reactions and exothermic reactions in the context of a chemistry lab. So here in this image, we can see that there are two beakers. Oh, actually, sorry, my mistake. There are two Erlenmeyer flasks. Both of them have a substance inside. In the first one, the substance is very hot. Okay? If the substance is hotter than the surrounding, it generates heat. Okay? So all of these little arrows pointing outwards is pointing out into the environment. Because heat energy has to go somewhere. Okay? It usually doesn't say trapped or contained within the object. They're always being passed along or transferred. Now, at the other end, if you have a substance that is cooler than the surroundings, heat energy from the environment will seep into that particular substance. Or from the substance perspective, it's absorbing heat from, again, the environment. So if we were to touch these Erlenmeyer flasks, the one that's undergoing through an exothermic reaction, from our perspective, would feel hot. So things that feel hot are generally things that are going through exothermic reactions. Things that are going through an endothermic reaction is absorbing heat. So when you touch that substance, it actually feels cold. But the only reason why it feels cold is because it's absorbing heat from the environment. And when you're touching that object, you are actually part of the environment. So it's absorbing heat energy from your body. And if heat energy is leaving your body, that's why you feel cold. So this is actually a good lesson here, because cold simply means the absence of heat. It is generally a feeling. It's nothing that we're measuring. What we're measuring is how much heat is present. And if there's very little heat present, then it's considered cold. Most of the time we have trouble measuring coldness. For example, wind chill. Wind chill gives us a sense of how cold something is, but it doesn't really measure what the actual temperature is. When you're measuring temperature, you're actually measuring how much heat is present. So let's take a look at a different direction. We're still talking about heat energy, but let's talk about heat energy in the form of phase changes. So here you'll kind of recognize our standard heating curve. So if we're going from bottom up, we're talking about heating. If we're reading the graph backwards and we start from the top and moving downwards, then we're looking at a cooling curve. So on this particular curve, they've overlapped a phase change diagram so that we can see exactly what is happening to a substance. So if we start with the solid and we're heating it, we have to actually add energy. So the melting process is generally endothermic. You have to absorb heat in order to cause those molecules to move farther away from each other. So heat here is being absorbed. As a liquid, it will continue to absorb heat. So even the vaporization or boiling process is also endothermic. But once we reach a gas, we don't go through any other phase change. Okay? We're ignoring the fact that we can actually turn it into plasma because most things on Earth kind of just stop with gases. So let's look at what happens when you cool it. When you cool a gas, heat has to be released from the gas molecules. So here, heat is released. So if heat is released, the condensation process is actually exothermic. And as a liquid releases heat to turn into a solid, it too is exothermic. So all of our physical changes can be based on endothermic and exothermic properties. So we'll come back to these specific ideas again. Let's move on to some examples of exothermic and endothermic processes. Our first example of an exothermic process is, of course, combustion reactions. Okay? Things that produce fire. Okay? Fire tends to be exothermic because it releases heat into the atmosphere. Now, where the heat comes from, okay, because it's exothermic, it releases stored energy. Within bonds. Because we're breaking the bonds and we're forming new substances in a combustion reaction, this is a good example of a exothermic reaction that is linked with a chemical change. But not all exothermic reactions have chemical change properties. Okay? We also have exothermic reactions based in physical changes and physical properties. So when we look at our next example, look carefully at what's in the image. We can tell that there's a large body of water, and there seems to be some kind of gas coming from its surface. Okay? And if you look very closely, you'll see that there's a bunch of ice, okay, overflowing this lake here. Okay? So obviously, we're in the middle of winter, okay, and what's happening is that this lake is about to be frozen. So let's call this freezing lake. When this lake freezes, heat energy is released. It's released because in order to go from a liquid to a solid, that extra energy has to be taken out so that the molecules can come closer and closer together to form that solid. Okay? And because we're talking about water turning into a solid, it gives off heat that sometimes look like steam is coming out from the water. So we are getting rid of heat in this process. And this process, of course, is a physical change. If you actually go down to the Forks right about this time right now in November, you'll notice that in some mornings you'll see some, gases escaping the surface of the water. Well, that's actually just heat energy that's being released. And it's actually a pretty sight. So we know that as it's releasing energy, over the next couple of days, the water will eventually freeze over. Now, for our last example of exothermic reactions, we have a hand warmer. I'm sure you've seen these around because they're actually quite popular. They're very convenient, in fact. All it is a liquid substance that's encased inside this package. And you'll notice that there's a metal disc inside this package as well. This metal disc, when you press upon it, releases what we call a seed crystal. So it releases a substance that causes the liquid to change into a solid. So the metal disc releases a chemical to cause the liquid to turn solid. And as we know from the above example, when a liquid turns into a solid, heat is released. So because heat is released, it is therefore an example of an exothermic reaction. Moving on to endothermic. Most of these particular reactions, okay, when you're touching them, the object, they should feel cold. Okay, and the first example here is a no-brainer. So when we actually look at ice melting, ice melting is basically a solid turning into a liquid, and it requires the addition of heat. So if heat is being absorbed, what ice is actually doing with that heat, okay, as it's being absorbed, heat absorbed is used to break bonds. They want to break the bonds that keep a solid a solid. So as those bonds break, they gradually become liquid. So therefore, solid turns to liquid. And because you're absorbing heat energy to do this, it's considered an endothermic reaction. In our next example, we find a plant absorbing sunlight. Plants absorb sunlight for photosynthesis. Okay. And of course, they use photosynthesis to make energy for the plant. So this is a chemical reaction or a chemical change. So if they're absorbing, this is the only reason why it's considered to be an endothermic reaction. So it converts sunlight to food energy, like sugars. Okay. Our last example deals with baking and cooking. Most of the time, if you use examples like baking and cooking, they are very appropriate for endothermic reactions. In this image here, we're taking raw cookie dough, and we're adding heat to make baked cookies. This, of course, is again another chemical change. Okay. Once you've baked those cookies, it's impossible for you to get it back into its raw state. Okay. And because it requires heat energy to do this, to cause this chemical reaction, this is a good example of an endothermic reaction. So we've gone through several different types of exothermic examples and endothermic examples. There are actually many, many more, and I do suggest that you try and develop your own examples of endothermic and exothermic reactions. Just look for them in nature because they're pretty easy to find. But remember, when you are explaining endothermic reactions and exothermic reactions, make sure you establish the object or the reaction. Okay? Let people know which direction energy is moving towards. Is it being absorbed by the chemical substances or object, or is it being released? Okay? So there's always a relationship between the object or the chemicals and their surrounding environments. Alright, that's all I have for today. Hope to see you guys soon.